All right, section 2.6 is going to be one of the last sections where we're kind of revisiting some things that we've talked about in the past. Until we get to like chapter 3, we'll be talking about probability, but probability is generally a topic that always needs reiterated. But we're going to start finding that we're going to start talking about some concepts like standard deviation, variance, z-scores, those types of things that you've probably never experienced before. So this is going to be one of the last kind of sections where there is some familiarity from previous courses, but that familiarity is going to quickly dwindle as we progress through the next couple sections. 2.6 skewness and the mean, median, and mode. Okay, I've used this word skew before in class, but we've never really formally defined it, so we'll take the time to do that here in a moment. But here it says consider the following data set: 4, 5, 6, 6, 6, 7, 7, 7, 7, 7, 7, 8, 8, 8, 9, and 10. It says this data set can be represented by the following histogram. Okay, each interval has width 1, and each value is located in the middle of an interval. Okay, so not sure, what this data is representing, but we were able to categorize it this way, and we see that the shape of this thing looks very symmetric. Okay, and meaning that if we come to the middle of the graph and fold there, you guys have talked about, parabolas being symmetric and that sort of thing, polynomial functions being symmetric. Same idea here. If I fold on that dotted line, the left-hand side of the data falls on the right-hand side of the data. The histogram is symmetric. That's a special type of data, and eventually we will move away from the histogram image, and we will look more to something that looks kind of like this, which would be what we call a distribution curve, but still symmetric. Okay, so whether we're looking at the histogram or a curve, we've got this idea of symmetry. It says in this data set, the mean, median, and mode are all 7. Okay, so if I were to take these quantities and run them through Excel real quick, we should get those 3 measures of central tendency. Okay, so I'm going to do that real quick for us. Okay, I think I've got the data in here. I don't have any errors with it. So if I say, average of A1 through A16 here, it gives me 7 back. If I go mode of A1 through A16, it gives me 7 back. And if I go quartile of A1 through A16, it's quartile 2 for median, and I get 7 back. So we see that all 3 measures of central tendency are identical here. Okay, when that happens, it is said that the distribution is symmetrical. Okay, so in a perfectly symmetrical distribution, the mean, median, and mode are all 3 the same. It says if the distribution is symmetrical but bimodal, the mode will differ from the mean and median. Okay, so those are something like, let's say that we had, let's give you a quick glimpse of something like that. I'm going to use just a curve instead of a histogram, but if I had something that did something like that, okay, if I took the median and the mean of this data, it's going to show up there, but that would be a mode, and that would be a mode because these are frequencies over here on the left-hand side. So because the modes are 2 quantities, this is bimodal, but it's still symmetric. If I folded there, left-hand side is going to fall on the right-hand side, and the mean and the median in the middle. Okay, so we can have what we call a bimodal symmetrical distribution. This is a unimodal symmetric distribution. Okay, with these things. Okay, so in this situation, because all three of these values are the same, it would not matter which value. There's not a difference in which measure is the better approximation or the better measure for the center. Okay. Now, when we have data that is skewed, and we talked about this yesterday with a specific example, that your mean can be skewed or is less resilient, was the word that was presented yesterday. The mean is less resilient to outliers. Okay, so when it says we have a left skewed distribution, it says it's a distribution of data that has a long left tail, and that means that the hump is going to be to the right. Okay, so when it says left skewed distribution, the left part is talking about where the tail is. Okay, sometimes referred to as a negative skew. So this is my tail. Okay, so call this a left skew. Okay, and what that is saying is, if you remember yesterday, if I have, let's say we have some data values of, let's say like 100, 103, 104, and 108, and then I have an outlier of like 4. Okay, kind of think what's going on here is this average, this mean, this arithmetic mean, arithmetic average is going to be pulled to the left. Okay, so your mean, okay, if our mean was in the middle, mean, let's say we had a symmetric distribution, our mean, median, and mode are all in the middle. If there is a data point that takes and pulls this side, stretches that side out, pulls it all the way out, skews it out, what that's going to do is it's going to, because the mean is less resilient, it's going to pull the mean with it. Okay, so if I were to, do the average of these 4 numbers, so 100, 103, 104, 108. So I take the average of those, C1 through C4, gives me 103.75. So you see there, with just using those 4 numbers, my average is in that, is representative or symbolic of that data. But if I now add 103, 104, 108, 100, and then the number 4, and ask for now the average of that, so D1 through D5, you see that now my average has gotten, my mean has now shifted from about right here in the data to now over here in the data. So the mean has been pulled over towards that value of 4 in my data. So the mean no longer is the best descriptor of the middle. Okay, the median now is or I want to say the middle center. The median is now the best descriptor for the center. Okay, when we do that, the mode is then to the right. So it goes. So the mean is less in the left skew. The mean is less than the median, which is going to be less than the mode. Okay. Now, obviously, I have no mode here, so you do have distributions that do not have values that repeat. So they're all showing the same frequency. So we would say we have no mode in that situation. Now, if I had a number, we did this yesterday. I think we had a situation where like we had people making like $30,000 in this town of 50 people. Okay, but one of those 50 people made 5 million. Okay, and what happened is if I looked at the median. Okay, so if I have this distribution, this distribution would be pulled out kind of like this, to where now my mode and my mode would be back here. This would be my median, which would be the 30,000. That's going to be my middle value, and actually the median and mode would be the same in this situation. And then like 5 million was way out here. And what we did is when we figured out what the average was using that outlier, the average or the mean was like $148,000 or $128,000. But everybody except for the guy that made $1 million was making $30,000. So that mean was pulled because it's not resilient to outliers. It's vulnerable to outliers. It's volatile to outliers. So it is easily manipulated, easily altered by one outstanding outlier. So in this situation, again, the median would be better measure for the center. Okay, so when we're asked questions about what is going to be the best measure of center, we first have to determine, okay, well, what type of distribution do I have? Do I have a symmetrical distribution? If it's a symmetrical distribution, they're all the same, then the argument is mean is going to be the best center of data or measure of center, because there's going to be so many more things calculation-wise, formula-wise, analysis-wise that we can do with the mean that we can't necessarily do with the median and the mode. Okay? If our data is skewed in either direction, then the answer is the median is the best measure of center, because the mean is less resilient. Okay, the median is not affected by outliers. Okay, because it's not based on quantity, it's based on position. All right, so the next says, and you're going to see some examples like this, is analyze the distribution of the following scenarios. Okay, so we have to kind of think in our minds, what would really be going on in this situation? Is there going to be any outliers? Okay, because that's really what's happening here, is that these skewed distributions are developed because of the impact of outliers. So if I think about the salaries of, and let me rephrase this, let's not say all teachers, let's say all employees. Well, let's rephrase. If I say all teachers, okay, let's leave it as all teachers. We're going to have teachers that are, let's put our table here with our frequency. And I think in our district we have about 100 teachers. We've got teachers that are making, our base salaries, and it's like the mid-30s. Okay, so we got some teachers down. We got less teachers down here. Okay, a lot of our teachers are. So in terms of like years of service, most of our teachers are kind of in their, I don't know, I'd say maybe 12 to 25, 28 years. And we could maybe analyze that data a little bit more. We could actually maybe find that stuff on our website, or it's public knowledge. So, but let's say we have very few people down here making, the base salary. A bulk of our teachers are here in the middle. Okay, so, and then we also have very few teachers that are at the highest scale on the pay scale, the highest level, making the most money. Okay, so what happens here is that we have a distribution that would look kind of like that. Okay, and that's going to be a symmetric distribution. Okay, So the salaries of all the teachers in the district is going to be a symmetric distribution. Now, if we did this, if I replace this with employees, and let's say that we talk about employees with certifications. So this is talking about teachers, administrators, superintendents, that kind of thing. Okay, treasurers. Not talking about janitors, maintenance, that sort of thing. If that's the case, okay, so teachers, administrators, all that kind of stuff, you're going to have obviously the same data as our teachers. Okay, but if I'm talking about in terms of money, so I'm just going to use this symbol for showing that money is increasing based on the further you get on this graph. Okay, we've got, like I said, we've got a few teachers down here that are making kind of the base salary. Okay, as we move on, we got more teachers that are making more and more. Okay, but eventually that kind of plateaus off, and as we get further and further over here, we get less and less teachers making large amounts of money. But we do have people like treasurer, superintendent, administrators that are pulling the mean. Okay, so a superintendent's salary, a administrator's salary, those things. So let's say that like the average salary probably for our district would probably be maybe in the $60,000 to $70,000 range. Okay, but administrators, superintendents, treasurers, they're making upwards of $90,000, $100,000, $120,000. So those are outliers. Those are pulling that mean over here. Okay, and is not a great center of data. Okay, so when you're talking about looking at like situations, like let's say we look at the and I'll take a large corporation, take Amazon, and say we want to look at the salary of Amazon employees, and we add Jeff Bezos into that. Okay, well the dude's worth like $80 million $80 billion. Okay, he's a drastic outlier, which is going to pull the mean. If we keep him in the average and determine the salary of employees, that is going to drastically heighten the average and make it skewed. It's going to make it non-representative of the bulk of the data. Okay, meaning the mean is susceptible or less resilient to his salary because it's such a great outlier. So when there are outliers and it asks you to discuss, what kind of distribution it is, if we're talking about salaries, income, those types of things, those are going to be normally skewed to the right like this. Okay, because outliers, large incomes are few, but the size, you don't have a whole lot, you don't have large frequency, but the size of the income is going to pull that mean away from the center. Same idea happens in something like this. It says the scores on a third grade reading test completed by graduate students. Okay, scores on a third grade reading test completed by graduate students. Okay, are you going to have very many people? Are you going to have very many people that are performing at a low level? Okay, so let's say this is my level of proficiency here. Okay, and here is my frequency. I'm not going to have, if graduate students and they're taking a third grade reading class or test, I'm not going to have very many people here at the low level. Okay, I'm not going to have very many people. All right, let me rephrase. I'm not going to have very many people at the low level, but in terms of proficiency, if that's the highest proficiency, I want to have most of my people, most of my scores over here. Okay. This thing's going to be skewed because of the performance. Most likely, I'm going to be high performing on this because the test is easy per these people's skill. So I'm going to have a lot of high performers. If we talk about maybe the idea that like everybody ace this thing, okay, we can have what we call a uniform distribution. I mentioned this, but if I have a distribution that is flat across, everybody performed the same skill level, okay, so something like maybe it was a histogram and all mine look like that, okay, all my data plots look like that, we call that uniform. Okay, we'll talk more about that in greater detail somewhere else. If we look at option 3, says the distribution of weights of a sample of 7th grade males. Okay, if I think about think about that situation. Is there anything in that situation kind of analogous to like salaries or analogous to like a test being very easy for a intelligent group, or a test being very difficult for unintelligent group? There's nothing in here that says that I can pinpoint having outliers. So in a situation like that, we're going to make the assumption that we've taken the sample and we've done it randomly, that we get this distribution here. We get a symmetric distribution. I gave the scenario that I have. Let's say we rephrase this. We say we have 3rd grade students taking a graduate assessment. So you have a less intelligent group taking a difficult test. You're going to have a higher frequency of people doing worse on that test, and you're going to have very few people. Remember, this y-axis is your frequency. So out here doing really well, you're going to have very few people. Okay? So this data would be skewed to the right. Okay? Down here it says identify the measure of central tendency that measures the center best. Okay, so I'm going to look at this here, and it says heart rates of a sample of adults, and I look at this and questioning, okay, what is this distribution? What does it look like? And to me, this distribution looks like it's symmetric. So the mean, median, and mode are all going to be here in the center. Okay, so for this situation, the mean is going to be the best measure of center. Okay, if I look at this one here, the heights of players on 2 opposing volleyball teams, same thing kind of happens here. Okay, it looks symmetric to me. Okay, so the mean is going to be the best. Come down to this one here. Okay, now this one here, if we think about this, it's the tail is to the right. So this is skewed right. Okay, which means there's an outlier out here, which means my median is back here somewhere, and my mean has been pulled away. When it's skewed to the right, the mean is pulled away towards the outliers, towards the tail. And when that happens, the median is the best descriptor for center. Okay, so median would be my best here. Okay. Also, when you think about what's going on here, okay, these responses, okay, I just looked at the graph. I didn't really look at what graph was talking about. These responses are nominal. Okay, when things are nominal or ordinal, the mean, I mean, how do I go about doing the mean of words? How do I average words? I can't. So in that situation, the mean isn't even able to be determined. So the median would be for that reason alone, the best describer for center. If I look at this now, and this is the one that people struggle with. If I look at this, people are like, oh, this looks symmetric. This looks like that shape at the top. But what's happening here is that guy right there being an outlier. So what happens is that mean, okay, if it was symmetric, the mean, median, and mode would all be right here in the middle, okay? But now, because of this outlier, the mean is pulled out to there. The median will be there. And if there is a mode, the mode would be there. Okay? So because the mean was volatile to that outlier, was impacted by that outlier, in this case the median would be the best center or measure of center. Okay? Let's see what time we got here. All right. So I want to talk about weighted averages a little bit as well. Weighted averages. Okay, still going to use X bar for average. Okay, so this is staying in line with what we talk about with sample means. Still using the summation notation with the index starting at 1 going to n. But now we have X sub I, which is the data point, now times W. W stands for the weight. Okay, and now instead of divided by the sum, or sorry, divided by n, we're going to divide by the sum of our weights to find our weighted average. Okay, so just got a couple examples here. I think maybe the first example is probably the easier one, is the second one here, which these aren't in your notes. You might have to write these down. It says an instructor grades exams 20% for a term paper, 30% for a final exam, 50%. All right, sorry, rephrase it. Exams are 20%, term paper 30%, finals are 50%. So the student had grades of 83, 72, and 90 respectively for his exams, term paper, and final. Find the student's average. Okay? So what we have to do, if I want to find the average, okay, I'm going to take the sum of the data points times their weight. Okay? So when it says respectively, this is something we talk about in geometry. That means in the order that they were identified. So when it says 20% as the exam grade, that was the first percentage given, match that with the first grade given. So 20% and 83. So what I do is I take the 83, which was the X sub I, and I multiply it by its weight of 20%, so 0.2. Okay? Then we're going to add to that, because it's summation, 30%, which is for the term paper, second percentage listed. So now I go second percentage, or second grade down here. So I'm going to go 72 was the data point times the weight of 0.3. And now I'll do the same thing for the exam and the score on it. So 0.5 times 90. So that's my numerator. Okay, that's the sum of the individual values times their weights. And now add or divide by the sum of the weights. So in this case, it'd be 20 plus 30 plus 50. So in this case, 100%. Okay, or 1.0. If, let's say that we were in a situation where maybe the final exam hadn't taken place yet, so your denominator doesn't always have to be 100. Okay, if the final exam had not taken place yet, my denominator would just be 0.5 because of the weights that had been used so far. So that's something that we see right now in our progress book with our class weights. Because our final midterms haven't been calculated, the way progress book is doing our calculations is the denominator is just the homework and quiz stuff that we've been doing. So I'm going to just grab Desmos here real quick. So what do we have here? 83. 83 times 0.2 plus then 72 times 0.3 and then plus 90 times 0.5. So this individual finished with an 83.2 for the course. Something that might be of benefit to you is kind of understanding how we do this with a weighted GPA. The scenario here just says students received an A in English, for, which is a 3-credit class, credit hours or however you want to view it. A C in Intro to Psych for its 3-credit class, B in Biology, and a D in Stats. Okay, so it's assuming that we're on a 4.0 grade scale, so an A is worth 4 points, a B with 3, a C with 2, and a D with 1, F with 0. This can get very kind of convoluted and messy when you get into like college classes where like a 90 like a 90 or 100 to like a 97 is an A plus, and is worth for like a 4 point or 4. And then as you get lower, so sometimes like a 93 to a 90 is considered like a 3.9. So they kind of stagger it, and a high, an A plus is in some math classes, or not math, college classes, is a greater weight than a lower A, like an A minus and an A plus, or a B minus and a B plus will carry a different weight. So it gets kind of messy in those situations where if I'm dealing with grades here, okay, so the credits are going to be my weight. My grade is my individual data point, and in this case, they're saying an A is worth 4 points, a B is worth 3 points, a C is worth 2 points, and a D is worth 1 point. Like I was saying, in a college class, like an A might be with 4 points, but an A minus is like 3.9. A C might be worth 2, but a C plus might be with like 2.9, and a C minus might be maybe like a 2.1, whereas maybe a C is a 2.5 or something like that. So we can be more kind of interval in regards to those values. So when I want to find the weighted average here, the GPA, okay, I'm going to take the sum of my X values times their weights, and I'll divide that bit then by the sum of the weights. Okay, so I'm going to take my 4 for my A, I'll multiply that by my weight of 3 credits. Then I'll add to that the 2 that I got for my C, and multiply that by my weight of 3. The same thing for my B. My B now was a data value of 3 multiplied by my weight now of a 4. And then the D is 1 times the weight of 2. Okay? So now I'm going to then divide that by the sum of my weights. The sum of my weights are how many credit hours that I'm actually enrolled in. So it's 6, 10, 12. So 12. And I can divide that out then. So we should be able to do this quickly. We have 12 plus 6 plus 12 plus 2. And we'll divide that then by 12. and there's the GPA that this individual is receiving. So those are weighted averages. You see a couple of those in our homework. Not a huge deal. Just if you have any questions or anything, please don't hesitate to ask. We will be spending several days on 2.7, which is going to be the next thing that we do is standard deviation, variance, z-scores, and my plan is to, at the conclusion of 2.7, we'll have a unit test. Okay, so that will be coming up probably mid to late next week. Just so you're on the lookout for that. And I'll send that out in an email as well.